Hi everyone. This video is going to be about polar coordinates for double integrals, and it's going to be a pretty short video because polar coordinates are just a special case of what we've already been doing in the previous section, where we looked at non-rectangular regions. The only thing is this is just going to be good for regions that have some kind of circular component to it. So if our regions look anything like this, or maybe we'll look at some rings as well. The idea is that if the region looks anything like this, then polar coordinates are going to be what we want to use. It'll usually make this a little bit easier. So like I said, it's just a special case of the last section where we looked at non-rectangular regions. And I want to think about some of the decisions that we made for non-rectangular regions. One of which is we can say, will changing the order make integration easier? So that I mean, is dx dy the better option, or is dy dx the better option? We can also think about that's not much of a decision, but we can't use Fubini's theorem. That is to say, we can't simply just switch the numbers on the two integrals because we've got some functions for non-rectangular regions. We want to think about what the easiest way is to put constants on the outside integral. On the outside integral. So we saw in the last video that last example was a demonstration of how putting the constants on the outside, sometimes the shape of your region is just going to make that a lot easier when you put the constants on the outside. So I'm just going to add the last thing for this non-rectangular regions, which is we can ask ourselves, will polar coordinates make our calculations easier? And this is pretty easy to figure out if you have a circular region like the ones I drew in the beginning, or something that's some section of a circle. So this would kind of be the most extreme example where we have not a full circle, just a section of a circle, and then a sort of section of the donut shape that you would make. So if your region looks something like this, then we can talk about using polar coordinates for that. Just a quick reminder of polar coordinates. So the equations that you're going to be using for polar coordinates, we have x squared plus y squared is equal to r squared. So that's the conversion that we can make. The rest of these, you can think about these as being based on this right triangle here. So if you kind of picture a unit circle here, this is your y, this is your x, and this is your r. So Pythagorean theorem says that x squared plus y squared is equal to r squared, and we can also write, I'm going to try and insert this into the middle of a video, but I made a mistake where I said x was equal to r sine of theta. It's actually x is equal to r cosine of theta, and y is equal to r sine of theta. And that matches up with this rectangle here. Last one that's used a little bit less frequently is that we can write that the tangent of theta, if we don't want to involve r for some reason, that tangent of theta is equal to, let's see, opposite over adjacent, so y over x. Those are the four big ones, and I think that's all you're going to need for your web assignment. I will say that this one at the top here, anytime we can write r squared as x squared plus y squared, if we ever see x squared plus y squared, use this one. Don't write r squared times sine of theta squared plus r squared cosine squared of theta. That's just going to be a huge mess. You could just be writing r squared. So definitely keep a lookout for this one, and that'll help you answer the question too. Will polar coordinates make this easier? If you have an x squared plus y squared somewhere in there, then the answer is almost always yes. Okay, so I've got an example for us to look at. So this one is asking us to find the volume under the surface. F of x and y is equal to cosine x squared plus y squared. One hint that you might be looking at a polar coordinates problem. Over the half circle region sketched here, it's a half circle, so that's the other way you can tell that you're talking about a polar coordinates problem. Okay, I want to start off just by talking about what this would look like in terms of x and y. So I'll start off by saying x is in between, looks like -1 and 1, and y is going to be in between. So we need some functions here, right? We can't just say y is in between -1 and 0, right? Because that would just be defining this rectangular region. And that's not enough. We can't just have constants here. We need to say the bottom surface, or sorry, not the bottom surface, the bottom curve is this circle here. So we want to write our circle here, and then the top surface is going to be, it looks like this one, which is y equals 0. So y equals 0 up top there, and then this circle, if you don't know the equation for a circle in terms of y, you can start off with x squared plus y squared is equal to the radius of the circle, 1. This tells us that if we solve for y, we get plus or minus square root of 1 minus x squared. And to answer the question of if we're talking about plus or minus, we're looking at the bottom half of the circle. So we're looking at all the negative y values. So we'll just use the negative 1 minus x squared. Okay. Again, we're going to be using polar coordinates for this, but I just want you to be really, really comfortable moving forward with seeing these circles here and all the different forms that you might encounter them. Okay, so if I wanted to set up this double integral, it would look up something like this. So I'm trying to find the volume under the surface, this thing. And let's see, we put this in terms of y, so let's put dy first, and then dx will be the exterior. We can set up our bounds. Right, y is in between this and this. And then our f of x and y is equal to cosine x squared plus y squared. I chose this example because trying to integrate this, so first step would be integrating this with respect to y, already looks like a nightmare. All right, like this would be an awful integral to try and do, especially with plugging this in and then integrating with respect to x, cosine squared. It's just really, really obnoxious to attempt. Can't use U substitution. Um, but if we convert this into polar coordinates, this region is going to be really, really easy to set up. And this surface that we're finding the volume under is just going to become cosine of r squared. And that's really nice. So I'm going to add just a couple more, or sorry, just one more equation and then a sketch of something just to help you remember what's going on with polar coordinates. So this one is if we have dx dy, right? If we want to convert that into polar coordinates, we want to have r dr d theta. So I think I'll have a separate video explaining why it's r times dr d theta. So for now, I'll just ask you to trust me, whether it's dx dy or dy dx, when we convert it to r dr d theta, we need to add that extra r in there. I will say I actually did a video, not a video, I did a little experiment one semester where I had two sections, and with the first section, I explained sort of all the theory and answered some questions about why we have this extra r in there. And with the second section, I just simply said, hey, when you have dx dy, you need this extra r, like a pirate, r. And that's all I said about it. I didn't draw the picture or anything. And when it came time for the exam, the section that I just said it's R like a pirate, they did a lot better. So, you know, I'll go ahead and explain the theory so you can benefit from both of them, but just remember this R in here. That's very important. R. Okay. The other sketch that I wanted to draw is basically the same as this. I just want to remind you that theta comes off of the positive x-axis and sweeps toward the y-axis, and that r just the lowercase r there. R is this distance that's measured from the center out to the radius of the circle. Right. So this one down here, if we want to talk about this one, it's got a radius of 1, the circle does. Theta in this case would be sweeping from starting at pi all the way over here, all the way over to 2 pi. So theta would be in between pi and 2 pi, and our r is going to be in between, since we want to sweep everything, not just the outside. So the outside has a radius of 1, but the inside has a radius of 0. So our r value is going to be in between 0 and 1. So here's where the radius is 0. Here's the radius at 0.1, 0.2, you know, all the way up to 1, and that'll sweep everything. Okay. So main point here, this as it stands is very difficult to integrate. But it would benefit hugely from converting to polar coordinates. So let's take everything we can and convert it into polar coordinates. Dy dx is going to become r dr d theta. This piece here, cosine of x squared plus y squared, is going to become cosine of, well, x squared plus y squared is equal to r squared. So we'll see if that makes things any easier. Another thing that you're going to be tempted to do here is convert this into polar coordinates, right? So we could write negative square root of 1 minus and then r squared cosine theta squared. But you're only making your life more miserable when you do this, right? And these are y values anyways, right? So there's no point in trying to do any algebra in these bounds. And I'll say that again because it's really important to um, think about this when you're doing polar coordinates. You're not making your life any easier. You're only making this integral harder if you try to plug in something for x, right? The whole point of polar coordinates is when I write this out, cosine r squared r dr d theta. The whole point of polar coordinates is if I have some kind of circular section for my region, r is in between 0 and 1. Right? We decided that based on the sketch, r is in between, right, 0 right here, and that stretches all the way out to 1. Sorry, that's a 1 there. Theta, this thing measured here, starts at pi and goes all the way around to 2 pi. So I want you to have an appreciation for how much nicer this looks, right? This is a rectangle, right? This is what we call a polar rectangle, where we have nothing but constants in all these spots here. That means we can use Fubini's theorem if we wanted to, right? It is a rectangle. And comparing this with trying to plug in negative square root of 1 minus r squared cosine squared of theta is a huge mess. This is way, way, way easier. So polar coordinates almost all the time is going to give you a nice polar rectangle like this. Okay. So we can actually go about solving this. So that volume is going to be pi, 2 pi, and we couldn't integrate cosine of x squared plus y squared, but we could use u substitution here. If we say u is equal to r squared and that means du is equal to 2r dr. We have a r dr here, so r dr is equal to 1/2 du. Okay. So this is going to become then cosine of u. R dr is going to become 1/2 du. And then this is a d theta. I haven't written these bounds yet here because I need to convert them to u values because now this integral is associated with u, not r. But in this example, it does not make a difference, right? So u is equal to r squared. I'll maybe write this. This is 0 squared and 1 squared, which is just 0 and 1. Okay. I'm going to pull that 1/2 out in front. Pi, 2 pi. And this integral is going to be, let's see, integral of cosine is just positive sine. So that's going to be sine of u, where u is equal to 0 and u is equal to 1. 1/2 is already put out in front here, and then I've just got a d theta. Okay, sine of 1, you shouldn't know what that is. If you do, I'll be very impressed, but you can leave this as just sine of 1, all right? Minus sine of 0, you should know what that one is. That one's just 0. Okay. Next integral, if we integrate cosine, or sorry, if we integrate sine, we should end up with negative cosine. Oh my gosh. Big mistake here. Sorry. This is just a constant, right? Sine of 1 minus 0. I don't know what I was thinking. Sorry about that. So the integral of sine of 1, this is just a constant. So this is going to be sine of 1 times the integral of any constant times theta is going to be equal to just theta, where theta is equal to pi up to 2 pi here. Okay, so we get our final answer. We might not know exactly what this is without a calculator on hand, but I think that's good enough. All right, so this is our volume under the surface, and I'm happy with that. Just to talk about a couple other regions that you might encounter, you can think about something that looks like this. So let's say that you are looking at a region that looks like this. This sort of half donut shape, where this is 2 right here, and this is 3 right here. For this one, we can say that theta is in between 0 and pi, and r is going to be in between starting at 2 and then ending at 3. The really common mistake that I see people make is they've labeled it like this, and they'll say, well, r is sort of in between -3 and 3, because they're thinking about r as being measured along here, which is correct, right? That is how r is measured. So I'm going to go ahead and write the correct answer here. It's in between 2 and 3. But if you think about r as not just this measurement starting at the origin and moving to the right here, you really want to think about r as being something that moves from the center and then just moves radially outward, right? So this point here is where the radius is equal to 0. This is all the spots where the radius is equal to 0.1. Right, this is where the radius is 0.2 and then 1, right? So kind of moving radially outward in any direction. That's how you want to think about r, right? Not just a straight line going from left to right. Okay. So I think the most elaborate that this gets in your web assigns, apart from one problem which I'll refer you to an example for, is something that looks like this. So they talk about this section right here, where this is a 45-degree angle. I don't need you to know sine and cosine of this 45-degree angle here. You should know how to figure it out, but you don't need to memorize that or anything. But if you want to talk about this region that goes from 2 to 3, this is halfway up to 90 degrees. So this is your x-axis, this is your y-axis. So for this one, theta is going to be in between, in radians, pi over 4 and pi over 2. For your r, same as the last one, that's going to be in between 2 and 3. One last thing to think about here. You might ask, well, what if it looks something like this, where I've got these 3/4 of a circle. Here, where this gets cut out. And what I'll say for this one is, let's say this goes to 7. Right? So r is definitely going to be in between 0 and 7 for this one. Right? It is a circle. So r is in between 0 and 7. And theta, we really don't have a really stellar way to accurately say what theta is in between, because it kind of starts at pi over 2, but it's not like it goes from pi over 2 to pi, right? That would be this section here, and that's not what we're trying to describe here. We're trying to describe 3/4 of a circle. So the way that the math works out is, as long as you can talk about it like sweeping all the way across, as long as you capture all of that in a sweep, then you can extend beyond 2 pi. So I'm going to call this starting at pi, and then this is 3 pi over 2 down here. This is 2 pi, and then this is going to be 5 pi over 2. So if you do it like this, 5 pi over 2, that's going to give you the correct amount here. I've also seen this where you say this is in between, let's see, negative pi. So starting at negative pi and then sweeping in this direction all the way up to pi over 2. If you look at the actual integral itself, the math is going to be the same either way. So just make sure that you're not accidentally just only counting for this quarter circle. So it's not going to be theta in between pi over 2 and pi. That's not sweeping through the full length. Okay, let me look at the time on here. I think I've actually got time to go ahead and give you the theory of why we have this relationship. So I'll try to make this quick, but why that extra r in there? So the region that we're drawing with these differentials, we can call this dA, right? And the idea is we have this little piece of area here that's got dimensions dx and dy. And for polar coordinates, and that's part of, like, you know, some larger region, right? For a polar region like this, the section that we're trying to call dA here is this square here. So that's our dA, right? And it's shaped a little bit differently than this. But if we think about the dimensions of this, from here to here, That's dr. It's just a small piece of radius, right? Or a small piece in the radial direction. But if we think about, let me make this a quarter circle. Right. If we think about this section here, let's say this has a radius equal to 10 or something like that. So the question is, how do you measure from here to here? Right? What's this distance across here? Because that's going to be what we measure respectively here. And this isn't just 90 degrees, right? We wouldn't just write theta here, or we wouldn't write pi over 2 here, because we need to account for how long that radius is, right? Like this piece right here is longer than, for example, this piece down here that kind of represents the same thing. So let me just draw a little bit. Right. Right, even though dr is the same, this piece stays a little bit different. So if you want to think about what this is part of the circumference. So the circumference is equal to 2 pi r, right? And the idea being that if you take this whole circumference of the circle, that's 2 pi radians times the radius, right? Times the radius r. So this little piece here is going to be whatever the radius of the circle is, right? Whatever the radius is at that point, dr. And then we're going to multiply that by how many radians it sweeps across there. So that's d theta. The result of that is that dA in this one is going to be dy times dx. And then dA here is going to be, we kind of treat this like a rectangle and say this is going to be dr times r d theta, or the way we usually write it, which is r dr d theta. Okay, so that in a nutshell is why we use the r in there and why we need that. So make sure to remember it. It's easy points on a 10-point problem. Just remembering that r is going to be worth at least 2 of those points. All right, we'll see you in the next video.